Physics Lab 3 was called Creating the Orbit. For Physics Lab 3, we were tasked with observing a star of mass 2 times 10 to the 30th kilograms as it orbits a black hole. We had to find the mass of the black hole by using the calculated forces on the star as it orbits the black hole. In this example, the gravitational force from the black hole acts on the star. This lab helps us to understand the acceleration due to gravity as it applies to different planets or objects of large mass. There were many physics principles explored, including Newton's law of universal gravitation that gives the attractive force between two objects, where r is the radius if an object is close to the surface, but is equal to the magnitude of the distance between two objects if the objects are farther away. Newton's second law is utilized to see the changes in momentum and explain the relationship between velocity, time, and net force. Other important things to remember are that net forces are equal to the sum of the forces acting on the object, and in this particular example, the net force equals the gravitational force. Another concept introduced is Hawking radiation. Hawking radiation is the theoretical radiation emitted by a black hole. For the first part of the code, a few parts that were changed include the email address that was given to us, and I changed it to my Georgia Tech email. This influences the trajectory of the star. The star's mass was set to the value given to us of 2 times 10 to the 30th kilograms, and delta T was changed to make it 86,400 seconds between each data point. For the second part of the code, the net force was set to equal the change in momentum. The mass and the parallel and perpendicular components of momentum were calculated by rearranging Newton's second law, and mass was set to equal the magnitude of the star's position squared times the magnitude of F net divided by the gravitational constant times the star's mass. Additionally, the arrows were adjusted to show the components of the net force. The mass of the black hole was approximated to be ranging from 1.61 times 10 to the 34th kilograms to 1.53 times 10 to the 34th kilograms over the course of the GlowScript model. These variations are likely due to numerical errors in the positioning of the star, but additionally, a slight mass decrease could support the theory of the Hawking radiation that is given off by black holes. The sum of all the masses gave me 7.08 times 10 to the 36th kilograms. When divided by the number of masses output by GlowScript, which was equal to 450, you get an average approximation of the mass to be equal to 1.57 times 10 to the 34th kilograms. Additionally, other information output by the GlowScript code was the magnitude of the net force equaling 9.42 times 10 to the 28th newtons, the magnitude of the parallel component of the net force equaling 1.17 times 10 to the 28th newtons, and the magnitude of the perpendicular component of the net force equals 9.35 times 10 to the 28th newtons. Throughout this lab, the mass was found by rearranging Newton's law of universal gravitation. The parallel and perpendicular components of the net force were used to calculate the predicted mass. The average mass of the black hole was found to be approximately 1.57 times 10 to the 34th kilograms. The reason the average mass was found was because, due to Hawking radiation and computed numerical errors in the position of the star, the masses output were slightly different at each time step. This helps to show the relationship between momentum and force, as well as how the perpendicular and parallel components of forces are proportional to the net force. Lastly, the net force was found using both Newton's law of universal gravitation and Newton's second law. This lab focused on many aspects of momentum as it relates to force, but the components of net force are different than the components of the rate of change of momentum because force causes the perpendicular and parallel components of the momentum. This means that there must be a non-zero net force in order to create a change in momentum. Additionally, when asked if a different black hole left the motion of the observed star relatively unchanged, and the star is only affected by the gravitational force of the new black hole, we would be unable to tell the difference. This is due to the star only being affected by the acceleration due to the gravitational pull of the black hole. If the motion of the star remained relatively unchanged, there is no way to prove that the new black hole's mass is any different than the first black hole.